Hello everyone and welcome to our second video on impulse. Alright, going to be looking at another worked example for this video. Alright, and we're going to look at a different type of impulse question. Alright, we're going to look at how to calculate impulse through the representation of a graph. So here I have worked example 17 taken directly from the Ciabola textbook. Alright, and in this video, this example deals with analyzing a force graph. Okay, here we have a graphed force versus time, alright, in the graph, and we have different intervals, alright, for which the force changes over time. So the question says, analyze the force versus time graph provided and answer the following questions. What is the impulse for the interval 0 to 3 seconds? What is the impulse for the interval 3 to 6 seconds? And what is the change in momentum for the interval 0 to 6 seconds? Then, what is the impulse for the interval between 6 seconds and 20 seconds? And then, what is the impulse for the interval from 0 to 20 seconds? In other words, that last question there is what is the impulse for the entire interval? And the entire time interval is from 0 to 20 seconds. Alright, quite a bit of calculations here. Alright, so first question you might ask yourself is, okay, how do I approach this question? Alright, well, don't worry, I am going to show you. Step 1, we always identify what information is given and what is being asked for. Always. That is always step 1. Alright, so step 1, the graph of force versus time is provided. Great, we know that. And we are asked to determine both impulse and change in momentum from it. We know that the area under the graph is the impulse, and we can relate impulse to change in momentum with the impulse momentum theorem. Alright, so that's one thing we need to remember, okay, is that the area under, or we can say underneath, all right, a force graph or force versus time graph is equal to impulse. All right, and we also note that the impulse momentum theorem, all right, is mvf minus vi is equal to the net force or resultant force multiplied by time, or delta t. All right, that's what we know. Okay, that is the impulse momentum theorem. All right, so coming back to the information, we need to calculate the area under the graph for the various intervals to determine impulse and then work from there. So this is quite an easy, straightforward question. All right, not that difficult at all. All right, so now that we have step 1 down, let's have a look at step 2. Step 2 is determine the impulse for the interval 0 seconds to 3 seconds. All right, so we're dealing with the first part of this question. Now, we need to calculate the area underneath the portion, underneath the shaded portion. All right, and we've shaded the portion in orange there, which is the 0 to 3 seconds over there. Right, which is the 0 to 3 seconds over there. So we have a triangle here. And we know that the formula for working out the area of a triangle, we remember this. All right, the area of a triangle is equal to half of the base times the height. All right, now we know this from the graph. We can actually read it straight from the graph. All right, so we know that it's half 3, which is the base, 0 to 3 seconds. Our base is 3 times height. Right, here we have 3 right here. From 0 to 3, 0 to 3. So half 3 times 3, which is half of 9, is 4,5 newtons per second. Now, you might ask, where do we get newtons per second from? Well, over here, force is calculated in newtons. We know time is in seconds. So that's how we get the SI unit, newtons per second. All right. So the impulse is 4,5 newtons per second in the positive direction. All right, we are above 0, so we know our units are positive. All right, so we have calculated the first impulse for the first interval. Let's calculate the second impulse for the second interval, which is from 3 to 6 seconds. Now this is a negative. Now we need to calculate the area of the shaded portion under the graph. Now this is also a triangle with the base of 3 seconds because 6 minus 3 is 3. And the height is negative 3. Why is it negative 3? We're below 0. Anything below 0 on this graph is in the negative number region. So we're going down here. This is our height. The triangle is basically flipped upside down. And there is negative 3 is the force reading. Okay, so this impulse, half base times height, is going to be equal to half of 3, this 3 over here, times negative 3. So half of negative 9 is negative 4,5 newtons per second. And this is the impulse in the negative direction. Quite straightforward. All right, quite straightforward, quite easy. So now we know for this shaded one over here, it was positive 4,5, and for this one was negative 4,5. All right, now let's go calculate the impulse for the next interval. All right, now the next interval is what is the change in momentum for the interval 0 to 6 seconds. Now we are focusing on only these two shaded areas. We have calculated the impulse for both of them. So from the impulse momentum theorem, we know that impulse is equal to the change in momentum. We have worked out the impulse for the two subintervals, making up 0 to 6 seconds. Now we can sum them to find the impulse for the total interval. And as they have indicated to you there, the impulse from 0 to 6 seconds is equal to the impulse from 0 to 3 plus the impulse of 3 to 6 second intervals. And we know both of them were the same, going in opposite direction. So 4,5 plus negative 4,5 is equal to 0 newtons per second. So that's a positive number. So that must be in the positive direction. So the positive impulse in the first 3 seconds is exactly opposite, as I mentioned, to the impulse in the second 3-second interval, making the total impulse for the first 6 seconds equal to 0 newtons per second. All right, quite straightforward. All right, now that we've looked at that, let's have a look at the impulse for the next interval, which should be from 6 to 12. All right, let's have a look there. And then we're going to include also 6 to 20 seconds, all right? So we're going to calculate it now from 6 to 20 seconds. Now we have two shapes involved here, okay? So instead of breaking them up and doing them into separate questions, we're just going to include them in one calculation. All right, again, so from the impulse momentum theorem, we know that change in momentum is equal to impulse, and that is equal to 0 newtons per second. For the next step, we need to calculate the area of the shaded portion under the graph from 6 to 12 and from 12 to 20 seconds. So we have two rectangles there, and we know that the area for calculating a rectangle or square, all right, we know that this area, all right, of a rectangle or square, okay, they both have 4 sides. I'm just going to draw a square there, is length times breadth. All right, so over here from the 6 to 12 interval, right over here, we have 12 minus 6 is 6, so we know that is 6 over there. And we know that this length over here is negative 3. So impulse from the 6 to 12 interval is negative 18 newtons per second. From the 12 to 20 interval, we can see that 20 minus 8 is in fact 20 minus 12, sorry, is 8. All right, and the height was, or the breadth was 2. So 8 times 2 is 16 newtons per second. Now, to calculate the total impulse of the sum of the two intervals, so the impulse from 6 seconds to 20 seconds, right, we know we need to sum both of them up, and negative 18 plus 16 is negative 2 newtons per second. So we know that the impulse is 2 newtons per second in the negative direction because there's a negative sign in front of the 2. So if we had to quote for the entire interval, the impulse of the entire period, we know that for the first 2 periods, over here, the first 2 periods were in fact 0. The impulse were 0 for the first 2 periods. And for the next 2, it was 2 newtons per second in the negative direction. Hence, the impulse for the entire period is 2 newtons per second in the negative direction.